3.5. And we will go ahead and I'll put that at the top so that we'll know. And then I'll make the little correction there. Section 3.5 is over rational functions and their graphs. Okay, the first thing that I want to do is make a correction from 3.4, and it is over Descartes' rule of signs. Okay, so in your homework, I went ahead and reopened that homework up in case you had missed, like, I think it's like 9 and 10. I think there were only 10 questions in there, maybe. So, like, if you had missed 9 and 10 because I had made a mistake in the presentation of Descartes' rule of sign, I reopened it so you can go back and fix it if you need to. Most of you probably got it fixed fairly quickly after you read the explanation of why you were possibly wrong, okay? The problems that you had, it asked you to find it said determine numbers of positive and negative real zeros, okay? And then it would give you like f of x equals negative 8x cubed plus 5x squared minus x plus 8, okay? And this was actually a homework problem. I pulled it up. And so Descartes' rule of signs says that you look at it, you count the number of sign changes, and those are the possible number of positive real zeros, okay? That part is correct. Where there was an error, where I made an error telling you, was then I went, okay, it's either that or it's an even number less, okay? So it's not necessarily an even number less. You go down by 2. Or you go down by 4. You start going down by even numbers. So like in this first one, when we're looking for the positives, we actually take this function and we count the number of sign changes of those coefficients, okay? So if I go from a negative 8 to a positive 5, that's a yes. That was a sign change, right? Then if I go from a positive 5 to a negative 1, yes, that was a sign change. And then negative 1 to 8, yes, that was a sign change. So there's 3. You got that first part right. When you typed that in, you went, okay, there's 3. But then, based on my instructions of what I gave you, you then wrote 2. You said, well, there's 2. Because I said it's the next even number down. Guys, it's 3 minus 2. It's you take 2 from the whatever number's there, the number positive. Okay, so you go down by even numbers. So the next number should be 1. So there's either 3 or there's 1. The other misconception that I need to clarify there is I told you don't worry about listing 0. Guys, you can list 0. You need to. So like if you had 2, then you would tell me there's either 2 or there's 0, okay? You put the 0 there. That's where I first noticed, okay, why isn't it taking it? It should just be 2. And then it was like, no, you got to list 0. And then I was like, okay, well, what if we have an odd number? Some of you guys were putting like, well, it was 3 and then it was 2. Well, it shouldn't be. It should be 1. You're going down by even numbers. So if we'd had 5, we would list 5, 3, 1. You're going down by 2 or an even multiple every time, okay? So on the negatives, you do change the sign of x. So this becomes negative 8 times negative x cubed plus 5 times negative x squared minus a negative x plus 8. You have to plug in that negative x there, which that was fine. Told you that fine, just correctly. And then that's going to give me a positive 8x cubed altogether. Then I've got plus 5x squared plus x plus 8. Now we look at those sign changes. I went from 8 to 5. There's no change. I went from 5 to 1. There's no change. And I went from 1 to 8. There's no change. Okay, so the possible number of negative zeros, real zeros, is 0. Okay. I just wanted to clarify that it's not the even number that's right after the 3. You don't start listing even numbers, and then you do also list 0, okay, if you make it to 0. Where we stop is pretty much at 0, because like right here, if I subtract 2 from that 1, okay, that gives me a negative 1. We can't have a negative number of possible real zeros, okay? So there's the correction from 3-4 on Descartes' rule of signs. My apologies. That was all my bad. I was trying to rush it in there, get it done, and then I gave you misinformation. I did. That's all on me, guys. So I wanted to fix that, and I did reopen that homework. If you need to go back and fix anything in that homework, it'll be open until I think I put tomorrow night. Okay, the 3-4. Okay, let's start on 3-5 now. Let's talk about rational functions and their graphs. The first thing we have is, let's look at what a rational function looks like. Okay, it is of the form f of x equals p of x over q of x. So guys, you have pretty much one function over another. That's what makes a rational function. It's pretty much a function that's in the form of a fraction, right? Okay, and we start off pretty simple, and we've done this before. In example 1, they ask us to find the domain of each rational function. And if you'll remember, we found domain before, and we had a set of rules with those. And with that, it would be, okay, we would ask ourselves, is x in the denominator? Is x in a radical? And if not, then it was negative infinity to infinity, okay? So this section deals with all the functions who have x in a denominator, okay? So that's why, and we find that those x's in the denominator become very important. They tell us things about the graph, okay? So we start off with just looking at the domain. So in A, I have f of x equals x squared minus 25 over x minus 5. All right, so when we're looking for domain, we ask ourselves, is x in a denominator? Yes, it is here. And I know that when I have x in a denominator, that denominator cannot equal 0, right? Okay, so I know that x minus 5 cannot equal 0. I'm going to add 5 to both sides. That means x cannot equal 5. Okay, so when I go to list that domain, if I'm going to list it in interval notation, that means I can use any value except for 5. So we would list that as negative infinity to 5 united with 5 to a positive infinity. Remember that we need to make sure and use those parentheses there, because it doesn't actually equal 5. You can't be there. Like it's not actually equal to 5. Because the function is undefined there. So we have to use parentheses. If they ask you for it in set builder notation, remember set builder is the one that has the curly braces. We can simply write x such that, remember that straight line means such that x cannot equal 25. And you can list it that easily in Set Builder. I know the examples in the book, we're listing it both ways. I've not checked your homework problems to see if they want Set Builder or they want interval notation. So I'm going to list it both ways here. B, so that's my domain for A. B, we have g of x equals x over x squared minus 25. We start with our same old question of, is x in the denominator? Yes, it is. So that means that x squared minus 25 cannot equal 0. Okay, we're going to get x by itself. I'm going to add 25 to both sides. That gives me x squared cannot equal 25. I'm going to take the square root of both sides. Remember to put plus or minus when you're taking that square root of positive 25 there. So that's going to tell me that x cannot equal plus or minus 5. Guys, that means x cannot equal negative 5 and x cannot equal positive 5. They're all about the 5s today, aren't they? That's going to give me a rather long interval notation there. That's going to give me, I can use everything from negative infinity up to negative 5. Then I can't use negative 5, so I put that parentheses on there. I'm going to unite that with negative 5 to a positive 5, because I can use all the values between negative 5 and 5. And then I'm going to unite that with 5 to a positive infinity. Like I said, the interval notation there is a little long. If I'm using a Set Builder, it's actually easier. You can just say x such that x cannot equal negative 5 and x cannot equal 5. Okay? Can't equal negative 5, it can't equal positive 5. All right, and then we do have a C. And once again, we're still dealing with some 5s here. I get x plus 5 divided by x squared plus 25 this time. Okay. Well, do I have x in the denominator? Yes, I do. So I know that x squared plus 25 cannot equal 0. I'm going to subtract that 25 from both sides. And that's going to give me x squared cannot equal negative 25. Okay, some of you see where this is going. So that's going to give me the square root of x squared cannot equal plus or minus the square root of negative 25, which is going to be x cannot equal plus or minus 5i. Okay, guys, is that a real number? No, that's an imaginary number, right? So what that tells me is, can I pick any real number x and plug in there and I'm going to get an answer back? Yeah, there's no real number that I can stick in that denominator for x that'll make 0 in the bottom, right? Because think about it, you're squaring x. So anything that you square right there is going to make, any real number is going to come back positive. So we're going to have a positive number plus 25. We can't get a negative 25 out of a real number, okay? So that means that my domain, I can use any of my real numbers. I can have negative infinity to infinity, okay, is my interval notation. And then, of course, my Set Builder is x such that x is in. We use that strange little e for is in. And then we use the double R for all reals. You probably will not have to list it like that in Set Builder. It's just I've noticed in the textbook we're getting more into, like today, we'll talk more about that as x approaches negative infinity, or x approaches positive infinity, like we did on the end behaviors. And I was like, we need to write this like big math people, and I would say f of x then approaches a positive infinity or negative infinity. We do things like that today, okay? They have you listing things like that today. Okay, so that's my domain. I'm going to go ahead, and this is where we get to talking about how things approach things. What happens when x approaches a certain value? What happens to y? Okay, and we're going to go ahead and graph and look at the reciprocal function, which is f of x equals 1 over x. Okay, that's your rational function. It's known as a reciprocal. Think about when we take the reciprocal of 2, you tell me that's 1/2. Okay, when I take the reciprocal of 1/3, what I do, I flip it over, that makes 3. That kind of thing. We go ahead and look at the graph because, guys, reciprocal functions, rational functions, you talk about them in Algebra 2, but it's not like a linear function. It's not like a quadratic function or an exponential function. Those three, you know by heart when you get done with Algebra 1 and Algebra 2. And sometimes you know what the cubic function looks like. But lots of times, reciprocal and other rational functions are kind of skipped over in high school. They don't talk about them as much as they should. But here's what we have when we have 1 over x, okay? So we actually, you're going to discover that we actually have a horizontal, and what we call horizontal and vertical asymptotes at x equals 0 and y equals 0. So the way we write this, the way we talk about it, is we want to look at what's happening as x approaches 0 from different directions. So they will write things like, and you will too, as x approaches 0, and they'll put a little minus at the top. Guys, that means as x approaches 0 from the left. Okay? So you're coming at 0 from the left-hand side. So he's like, your little bug's over here, and he's coming at 0 from the left. Okay? What's he doing? What's the graph doing? It's going towards what? It's descending. He's going down, and those y values that are down are who? What y is going towards what?
Negative infinity.
Good, yes. So we say as x approaches 0 from the left, f of x approaches negative infinity. Okay? Now, let's say our little bug started, he's still coming towards 0, but somehow he got on the other side over there. So now he's approaching 0 from the right. He got up the next morning, he was like, I'm going to try out the other side of the neighborhood. And here he goes. Okay. Where is it going to take him this time? As he approaches 0 from the right, what's the graph doing? What's his road doing? It's going up, right? So f of x approaches a positive infinity. Okay? Now we can talk about like we normally do and like you have before, about when x approaches a negative infinity. You can leave your little bug on there if you want to. As x approaches, let's say, we can say positive. As x approaches a positive infinity, so that means he's going to the right. His x's are getting bigger, right? So as he approaches a positive infinity, what is f of x approaching? What is that function? So here's the bug. And that bug's going to do what? He's getting what? Closer and closer to y equals, 0. F of x approaches 0. Okay, so as x gets bigger and bigger and bigger, that graph gets closer and closer and closer to y equals 0. But it's never going to cross it because we have a horizontal asymptote there. It's a line it cannot cross. Because here's why. If I put 0 in for x, what happens? It's undefined, right? And then can I ever make y equal 0? There's nothing that, if I put 0 in for y, I get 0 equals 1 over x. There's nothing I can do to that numerator to make it equal 0. Because the numerator is always 1, okay? Now, as x approaches a negative infinity, okay, so he's back over here on the other side. Like this, here he goes. And what's happening? He's getting closer and closer to who again? 0. F of x, not in purple. F of x, once again, approaches 0. Okay, so those are characteristics of 1 over x. Let me see if I can fix them a little bit. Okay. Another one that we also look at and talk about is f of x equals 1 over x squared. Okay. Now, you can kind of tell he's going to look similar, but not quite the same, because what's happening? We always get back what kind of y's? Doesn't matter what kind of x I put in there, it's going to become positive, because we're squaring it. Okay, there's no way to get a negative y back out of there. I mean, there's just not. Okay. So this graph looks like this. And you can also tell it is symmetric about the y-axis. Okay, that makes sense. If I put in a positive x, I get the same graph as if I put in a negative x. Okay. We can list the same things here. As x approaches 0 from the left, what is f of x going to approach? So I'm coming in from the left, like this, guys. So where's he going? Where's y going? Where's that graph going?
Positive infinity.
Yes, f of x approaches, I shouldn't put equals. F of x approaches a positive infinity, okay? Now as x approaches 0 from the right, come from the right side, what will f of x approach? Positive infinity again, okay? And let's look at as x approaches a positive infinity. So x is getting bigger and bigger. And once again, just like in our other graph, what does he get close to but never cross? 0. Good. F of x approaches 0. And the same thing happens as x approaches a negative infinity. We get f of x approaches 0. All right, let's talk about how to pick out vertical asymptotes. Okay. Oh, good, I have one. All right. The line x equals a is a vertical asymptote of f if f of x increases or decreases without bound as x approaches a. Okay, and we're going to look. That's just a formal definition there. Okay, I'm going to tell you how to find one, how to find the vertical asymptotes. To find vertical asymptotes, Okay, first we're going to factor the denominator. Okay, we're going to factor the denominator, and we're going to factor the numerator. If it can be factored. Okay, so we're going to factor the denominator and the numerator. Check to see if the denominator and the numerator have any common factors. Okay? Now, I'm going to go ahead and throw this in here, and we talk about this one a little more in a minute. Well, we talk about wholes in a minute a little more, but they go along with vertical asymptotes and with the factoring, so I'm going to go ahead and include them right here. Just know we're going to come back to them, okay? So, we check to see if the denominator and the numerator have any common factors. Common factors become wholes. Then factors of the denominator that are not factors of the numerator become vertical asymptotes. Okay, so what you do is you take, guys, the whole concept is centered around the denominator. So I don't need you to worry a whole lot about the numerator. It's kind of just it's kind of like an accessory. It's needed to make the outfit, but the outfit can be found and worn without the accessory, okay? So the main thing that you're looking at here is the denominator. So you take that denominator and you factor that denominator down. Now, if it appears that part of that denominator exists in the numerator, that there's a factor there, like say x minus 2 is on top and x minus 2 is on the bottom, that x minus 2 becomes a whole. Okay, he doesn't become a vertical asymptote. But say you have x minus 3 down in the denominator, but you don't have that in the numerator, that x minus 3 is going to become a vertical asymptote. Okay, so it all has to do with what's in the denominator. Okay, now the numerator controls who gets to be a whole and who's going to wind up being a vertical asymptote, but that denominator produces and tells you, okay, these folks could be wholes, these folks could be vertical asymptotes, depending on what the numerator says, okay? But the denominator is the one that's responsible for identifying the people. That's why we deal with domain, because where it cannot exist is where the wholes and the vertical asymptotes are, okay? So let's look at an example. All right, example 2. It says, find the vertical asymptotes if any of the graph of each rational function. Okay? And we have 3 different graphs we're going to look at. The first one is f of x equals x over x squared minus 1. So what we need to do is we need to factor the numerator and denominator. Mainly, we need to factor that denominator, okay? So we've got x squared minus 1. You need to remember kind of in your head over here what x squared minus 1 really is. X squared minus 1 is really x squared plus or minus 0x minus 1. So I'm looking for, this is easily factored, I'm looking for what multiplies to be negative 1 and they add together to be 0. What two numbers are going to multiply to be negative 1, add to be 0? 1 and negative 1, because I know that 1 times negative 1 gives me negative 1, and 1 plus negative 1 gives me 0, okay? So this is going to become, I can't do anything with that x in the numerator, right? He's just x. So this becomes x over x minus 1 times x plus 1. Okay, now is where we look for, are there common factors here? Is there an x minus 1 in the numerator on top? No. Is there an x plus 1 in the numerator on top? No. So that means that both these factors are going to turn into vertical asymptotes, okay? So the next part, I go, all right, x minus 1. Well, I know they're going to be vertical asymptotes. Okay, so I've got x minus 1 equals 0 and x plus 1 equals 0. So I'm going to set them both equal to 0. I'm going to add 1, and that gives me a vertical asymptote at x equals 1. And then I'm going to subtract 1 and solve, and that gives me a vertical asymptote at x equals negative 1. Okay? That's all you really have to do. Now, later on, we use this to help us graph, okay? And I'm going to show you right now kind of what that looks like. Let me go over here to, since we don't have to graph it just yet, and it was x divided by x squared minus, did it go? Yeah, 1. Okay? So if we look, see how at x equals negative 1. Remember, x equals negative 1 is a vertical line. It's x equals a number. If we look right here, if I were to go over here and I were to graph those asymptotes, x equals negative 1, okay? And then I use x equals positive 1. So my blue and my green are my asymptotes in there. You'll notice those red lines are not crossing over them, okay? That's what you're looking for. And so when you go to graph by hand, you'll denote that with dotted lines, okay? Because they're not really part of the function. They're lines that the function doesn't cross over, okay? Let's look at B. B, same directions. We find the vertical asymptotes of any, if any, of g of x equals x minus 1 over x squared minus 1. Okay? All right, well, that numerator stays x minus 1. We've already factored x squared minus 1. We know what that factors into, right? So that's x plus 1 times x minus 1. Okay, this time, what do we notice? Both have an x minus 1. So that means my only vertical asymptote is going to be at x plus 1. So I've got x plus 1 equals 0. I'm going to subtract that 1, and that gives me x equals negative 1. Okay? Now, the part that has in common actually forms what we call a whole. Now, like I said, we talk more about this later, but it just kind of goes hand in hand, okay? Because you don't want to be sitting around going, well, what do I do with that other thing over there, okay? We've got x minus 1 becomes a whole, okay? If I add 1 that's going to give me x equals 1 is where the hole occurs. Now, since it's a hole, it's a point, okay? Since it is a hole, it's kind of like an open point, okay? The way you find the y that goes with it is if you were to cancel out the greens, the x minus 1, the one that makes the hole, and substitute that 1 back in there. So you would be substituting this into 1 over x plus 1. And that would be 1 over 1 plus 1, so 1/2. Then I have a hole at 1/1/2. Okay, is what happens. If we go, it's hard to see them. Okay, it's hard to see them on a graph. If I go over here, back to my graph, and let's, who did we still have x equals -1? We still had that vertical asymptote there. This is going to become -1, okay? Now, we're saying that we have a hole at what, +1, when x is +1? If I turn this into a table, you'll notice at x equals 1, what does it say? It says it's undefined. But what happens? It looks like it actually equals something there, doesn't it? You can't actually see the hole, all right? But when you graph it, you'll put an actual circle there at 1/1/2. Did we get 1/2? And there'll actually be a hole there. On your 84s graph a little better, and you'll see a glitch in the pixels, okay? And it is actually designed that way so that whoever is using it, the user is knowing that they're having to look for a hole, and it'll come up, it'll have a little glitch in it. I think I have an 84 emulator here, yeah. Okay, if I put in, let me go over here to y equals, and let me do x minus 1. I'm going to put that in, yeah, parentheses. Divided by, he's not liking that real good, x squared minus 1. Okay, and let's close that. Let's see. Okay, if sometimes you can see, okay, do you kind of see that little, like I can see the line, like the grid line coming through there a little more. If we go to the table, you will see that we do have an error at 1, okay? But if you actually have the actual calculator, you can kind of see a small break. See how the grid line comes through at 1 and the grid lines aren't coming through at 0.5 and 1? That's that small little glitch. The calculator is going, yeah, there's an issue there. You can't see it as well on an iPad or with the emulator, but if you have an actual 84, you can see the little, it's like a little nick in it, like the pencil mark got lifted right there is what it is, okay? That's your hole. But we'll talk more about holes later. We wanted the vertical asymptote here, okay? Let's look at C. Holes become very important when you get to calculus. They're points of discontinuity. Okay, so it's very important that you're able to find those later on. H of x equals x minus 1 over x squared plus 1. Okay, well, can we factor x squared plus 1?
Yes.
We can. We can't because, look, if we were looking at the domain for that and we set that equal to 0, I'd get x squared equals -1. That would give me x equals plus or minus I. So that means that the domain here is -infinity to infinity, okay? So we can use any x value that we want, and it's going to work. So that means there's no vertical asymptotes. Okay. There's no holes either. And we already took care of that. Okay, let's talk about horizontal asymptotes. Okay, the line, I'm going to give you a formal definition first. The line y equals b is a horizontal asymptote of the graph of a function f if f of x approaches b as x increases or decreases without bound. Guys, that's why we wrote over there on 1 over x and 1 over x squared. That's why we wrote things like as x approaches a positive infinity, f of x approaches 0. And as x approaches a negative infinity, f of x approaches 0. Okay, that's the line y equals 0. That's a horizontal asymptote at y equals 0. That's why we wrote those things. Okay, now there is a process for locating horizontal asymptotes. Okay, if, there's 3 cases here. If the degree of the numerator is less than the degree of the denominator, a horizontal asymptote exists at y equals 0. Okay? So what this is telling you is that finding horizontal asymptotes has to do with the degree of the numerator and the denominator. Vertical asymptotes has to do with their factors, okay? Horizontal has to do with their degrees, okay? So the highest exponent of the numerator and the denominator, okay? If the degree of the denominator is larger than the degree of the numerator, then it's at y equals 0, okay? Hence, y in 1 over x, that was at y equals 0, and 1 over x squared, that was at y equals 0, okay? All right, so let's look at a different case. If the degree of the numerator equals the degree of the denominator, a horizontal asymptote exists at the leading coefficient. Let me write that. At y equals leading coefficient of numerator divided by the leading coefficient of the denominator. So if I have 3x squared plus 1 over 2x squared minus 1, there's going to be a horizontal asymptote at 3/2, 3 over 2. And we'll do 1. Don't worry. Okay? Last case scenario, so we've talked about if the numerator is less than the denominator. We've talked about if the numerator equals the denominator, and this is the degree. Okay? Last one we have to talk about is the degree of the numerator is greater than the degree of the denominator. Okay? If the degree of the numerator is greater than the degree of the denominator, there is no horizontal asymptote. Okay, there is no horizontal asymptote. A slant can occur, but we talk about that in a minute. Okay, so this is how to find horizontal asymptotes. You got to look at the degree of the numerator and the denominator. If the degree of the numerator is less than that of the denominator, so the degree is bigger on the bottom, it's at y equals 0. Okay, because think about it. It's like 1 over x. Okay, it's at y equals 0. If they're equal, then you take the leading coefficient of the numerator and it's over the leading coefficient of the denominator. That's all it is. Okay? If the numerator is greater than the denominator, then there's not a horizontal asymptote. Okay? Let's try example 3. Example 3 says, hold on. I'm going to start writing example 3 here, and then I'll move it to the other page. Because it's not all going to fit, I promise. Find the horizontal asymptote if there is one, of the graph if there is one of the graph of each rational function. Okay. A. I have f of x equals 9x squared over 3x squared plus 1. Okay. So the first thing I need to check is the degrees of the numerator and the denominator. Okay. So what's the degree of the numerator?
Square.
Yeah, so 2. Good. What's the degree of the denominator?
So
2. 2. They are equal. What do I do if they're equal? It's the leading coefficient of the numerator. Who's the leading coefficient of the numerator? 9. Who's the leading coefficient of the denominator? 3. And what's 9 divided by 3?
3.
Good. So I have a horizontal asymptote at y equals 3. That's all you got to do. Alex, like, this is easy. Got this. Yeah, it is. It actually is. And this actually helps you when you take limits later on with certain rule and limits. Okay, that's A. Let's do B. B says g of x equals 9x over 3x squared plus 1. Okay, What's the degree of the numerator?
1,
1. What's the degree of the denominator?
2,
2. Good. Okay, so the denominator is bigger. If the denominator is bigger, what's my horizontal asymptote?
0,
Y equals 0. Good. And you can put that out there. Degree of numerator is less than degree of denominator. Okay, so Y equals 0. That was the first one that we did, right? First one we listed. Okay, and C, h of x equals 9x cubed over 3x squared plus 1. What's the degree of the numerator?
3,
Good. What's the degree of the denominator?
2,
2. So degree of numerator, in this case, is greater than the degree of denominator. Okay? That means, will I have a horizontal asymptote? Nope. So, no horizontal asymptote. Okay? Not bad. Let me talk about a slant asymptote real quick, and then we'll have then we'll look at graphing after the slant asymptote, and that'll finish up the notes. Okay? But let's talk about a slant first. Slant asymptotes have to do with the degrees, just like they did horizontal. They follow along with them, okay? Kind of like how the holes are a little add-in to the vertical asymptotes, okay? Slants are a little add-in with the horizontal asymptotes, okay? By slant asymptote, I just mean pretty much, they mean like a linear function that's not a horizontal line or a vertical line. So they mean a straight line that's not a horizontal line or a vertical line, okay? And it's an asymptote. It's a dotted line just like the other ones, and it doesn't, your function doesn't cross them, okay? So the graph of a rational function has a slant asymptote if the degree of the numerator is 1 more than the degree of the denominator. Okay, 1 more. Just 1 more. Can't be 2 more. It's got to be 1 more. Okay? The degree of the numerator is 1 more than the degree of the denominator. So, guys, what that means is if we have a vertical asymptote, then we're not going to have a slant asymptote, okay? Because vertical asymptotes take care of if the numerator is less than or the numerator is equal to. And then you know we don't have a vertical if the numerator is greater, okay? So if the numerator is greater and we don't have a vertical, we hop over here and go, well, do we have a slant? The only way we have a slant is if that numerator, the degree of the numerator is 1 more, 1, guys, 1 more than the degree of the denominator, okay? It can't be 2 more. It can't be 3 more. It's got to be exactly 1 more, all right? This is example 4, correct? Example 4 says find the slant asymptote of f of x equals 2x squared minus 5x plus 7 all over x minus 2. Okay, so the first thing that we do is we need to follow the process like when we check for horizontal asymptotes. Okay, so I'm going to say, what is the degree of the numerator?
Two.
Yep. And what is the degree of the denominator? One. Yeah, it's just one. Okay? So there will be no horizontal asymptote. There will be a slant since numerator is higher by 1. And here's how we do that. You start off, you use synthetic division. Or you can use long division. If you would rather divide them out by long division, saying x minus 2 into 2x squared minus 5x plus 7, you can. I'm going to use synthetic division here because it's easier, it's quicker. Okay, I know that 2 goes in the box, and then up top I have an x squared, an x, and a constant. So I've got a 2, a negative 5, and a 7. Okay, I'm going to bring down a 2, a 4 goes up, a negative 1 comes down, negative 2 goes up, and 5 comes down. Yes, you notice that we don't get 0 for a remainder. That's fine. We don't really care. That just means x minus 2 is not a factor of 2x squared minus 5x plus 7. That's not what we're checking for. Okay? You know that 5 is the remainder. So if you went to write this, you would write 2x minus 1 plus 5 over x minus 2, right? You've learned that when we divide, that's how we rewrite that. Here's the slant asymptote. You throw the remainder away. What's left is the slant. This is your slant. So a slant asymptote here is y equals 2x minus 1. Okay? So when we're finding that slant asymptote, divide, throw away remainder, what's left is the slant. Okay, that's what that says. I can show you this if we graph it. I'll also graph the 2x minus 1 in there, and you'll be able to see how the function doesn't cross that. So if I go over to, let's put it in Desmos, it was, yuck, let's see, I'm going to do that, I'm going to take away that. It would probably just be easier if I retype the whole thing, 2x squared minus 5x, and then I've got a plus 7, right? And then I have on the bottom x, deleted x minus 2, okay? Gonna move around a little bit. And then we said we had a slant at, what was my slant at? Somebody tell me.
2x minus 1.
2x minus 1. And let's change that color. How do I change the flipping color? Do y'all remember how to change the color?
You gotta say it.
Okay, thank you. Let's make him blue. I knew Alex Lexi know. Okay, so you'll notice my slant is the blue line, and the red line is never crossing that. It actually won't cross it down here, even though it looks like it's going to. Here's the rest of my graph that we didn't see, okay? The red is the actual function, but if you zoom in down here, what do you see? It never really hits that blue line. It's going to get closer and closer to it. That's your slant asymptote. Same thing happens up here, if I can ever get back up here. Dear Lord. Okay. There we go. We see the same thing over here. So there's our slant in there with that. Okay. Let's talk a little bit now. Let's talk about graphing. We still have time. We've got to graph some. The textbook actually gives you like a whole 7-step process of graphing. I'm not going to make you write that out. Okay, there's certain things that we need to look for. The only extra little thing I'm going to mention in there, because some of your homework does do it, it tells you to test to see if they're symmetric about the y-axis or possibly the origin. So that means the function is even or odd. Remember how when we did that a long time ago, when we tested about the y-axis, what do I change the sign of? X. And if I get the same thing back, then I know it's going to be symmetric about the y-axis. That will help you draw it, okay? So let's just start off with example 5. And the directions are pretty straightforward. It says graph f of x equals 3x minus 3 over x minus 2. Okay, so guys, rational functions are not something that you're accustomed to looking at. Okay, you're not accustomed to dealing with. It's not like when you see a linear or you see a quadratic, or even when you see a cubic function. You kind of already know what he should look like. We don't really when we're dealing with a rational function. So we take out our, pretty much what it is you take out your toolbox and you start building this house. You start building the graph. This is what you do. So since we started off the day with asymptotes, I would suggest we find some vertical asymptotes. We find some horizontal asymptotes. We find some slants. We find some holes. Find those things first. Then we're going to find our usual x-intercepts, our y-intercepts, okay? We're going to see if we can graph like that. If we're still not real sure, then we'll look and see if that function is going to be even, like it's symmetrical about the y-axis, okay? Or maybe the origin. Remember with the origin, what do? We change the sign of both for the origin, okay? So let's start off. Let's look for some vertical asymptotes. Okay, so I know when I'm looking for vertical asymptotes, I pretty much need to factor this, the numerator and the denominator. Well, that numerator will factor into 3 times x minus 1, right? The denominator is already x minus 2. So who I'm looking for here is at this x minus 2. He doesn't have a common factor with that numerator. That means x minus 2 will become a vertical asymptote, not a whole. So I'm going to say x minus 2 equals 0. So I have a vertical asymptote at x equals 2. That's important when I go to graph it. Okay? Vertical asymptote at x equals 2. Let's talk about a horizontal asymptote, since we talked about those today. Okay, let's see if we have any of those. So when I deal with my horizontal asymptotes, I ask you for the degree of the numerator, and you tell me that is 1. Then I ask you for the degree of the denominator, and you tell me that is also 1. Since they're equal, that means I need to put a leading coefficient over a leading coefficient. What's the leading coefficient of the numerator? 3. How about the denominator? 1, and that will give me 3. So I will have a horizontal asymptote at y equals 3. Okay. All right, so we've got our vertical asymptotes, we've got our horizontal asymptotes. We're not going to have any holes. We're not going to have any slants since we had a horizontal, no slants. Okay, let's talk about the easy one first. Let's talk about a y-intercept. Okay, whoops, we don't want to write in yellow. If I'm talking about a y-intercept, who do I need to set equal to 0? X, good. So set x equal to 0. So this is what I really have. Remember, f of x is the same thing as y. So I have y equals 3x minus 3 over x minus 2. I'm looking for that y-intercept. So this becomes 3 times 0 minus 3 over 0 minus 2. Okay, that's going to give me a negative 3 over a negative 2, which gives me 3/2. So I have a y-intercept at, if I list that as coordinates, I really have a y-intercept at 0, 3/2. Okay. I'm highlighting this stuff in yellow that I need to make sure I go back and graph. Okay. We'll put it all together. Start putting it all together. Whew, I'm running out of room. X-intercept, I can squeeze him in right there. I did not realize that I had that small of space left. I always do that. Y'all know that. Yana's like, woman, can't you figure out when you're running out of room? Hey, I can blame it on OneNote. You can just keep writing forever on OneNote. And I can also blame it on, I'm of the pencil paper generation. So, I could tell real easily when I'm running out. I can't on here. So you just keep writing. And I like GoodNotes better than OneNote. So, no, I can't use just keep writing them forever. I don't like the way it prints out. But then if I wouldn't use paper, I wouldn't have to worry about how it prints, would I? No. Okay, x-intercept, who do I need to set equal to 0? Good. Set y equal to 0. So I have 0 equals 3x minus 3 over x minus 2. Guys, here's an easy hack on finding a y-intercept, and you have a fraction over here. I'm not worried about what's going on in that denominator right there. The only way I can get this to equal 0 is if I have 0 in the numerator. So set the numerator equal to 0 and solve. So I've got 0 equals 3x minus 3. That's 3 equals 3x. That's 1 equals x. So I have an x-intercept at 1, 0. Okay, so let's see if we can put these down there. See what's going on here. Okay, to start with. So I have a vertical asymptote at x equals 2. So 1, 2, and I'm going to call, sure, I'll make them purple. That's there. Okay, and then I have a horizontal asymptote at y equals 3. Okay. Okay, so this old function's not going to cross over those lines. Let's see what else I have. I have a y-intercept at 0, 1.5. So right here. Okay, and then I have an x-intercept at 1, 0. Well, that doesn't do me a whole lot of good there, does it? I can kind of tell probably what's going to happen on that left-hand side. We're going to have some kind of going on, aren't we? Oh, for y'all, it's like that. Okay? Let's see what happens, though, on... Now, they do tell you that once you check to see if it's symmetric about the x-axis or the y-axis or who. Then you also, when you get down to it, make a t-chart, okay? Now, we've got our points over here to the left of x equals, what is that? 2, right? So let's see what happens over there at x equals 3 and on. I'm going to plug in, let's try 3 and see where that lands. If I plug in 3 for x, okay, and I'm just going to do it up here where I have space. I apologize. I'm going to say 3 times 3 minus 3 over 3 minus 2. That actually turns out really nice, doesn't it? What does that give me?
6 over 1.
Yep, 6 over 1. So when x is 3, I get 6. 1, 2, 3, 4, 5, 6. Okay. Let's see if when he is 3, 4, 5, 6. Let's try him at 6. Let's see what happens at 6. No, I don't like that one. Let's try. That's not going to be real good either. 15, 12. Let's try 5. That's a good thing about doing math like forever, that I can I do it in my head real quick, and so I can pick you some nice points. Okay, try 5. When x is 5, what do I get? I got 3 times 5 minus 3 over 5 minus 2, right? 15 minus 3 is 12 over 3 gives me 4. Good. So at 5, that was 2, 3, 4, 5. I get 1, 2, 3, 4. So you see, now, guys, when we had our rational functions, you know, they kind of make those wings, like that. Something's going on out there. So I predict that since I have these points and they're looking pretty much, I'm going to get the same halves kind of going on like this, right? That we get ourselves a function that looks very similar to this. Okay, we want to check him. Let's go over here and check him. Let's see if I told you wrong. If I treated you wrong there, I could have. You never know. Never know. Was this 3x minus 3 over x minus 2?
Yep.
All right. 3x minus 3 divided by, oh, that's just so wrong. That's not going to be the right thing, is it? Look, y'all weren't even going to stop me. You were just going to let me do it and go, you're wrong, must be. That's so wrong, y'all. There we go. Yep. And if we graph our our vertical and horizontal asymptotes there, what was my vertical? X equals what?
X equals 2.
Okay. And then what was my horizontal? Y equals 3? Yep. And you'll see how they sit, just like that. Is that what our picture looked like? Pretty much. Yep. Can y'all see them both sitting there together? Does it show you? Yeah, it does. Yep, there we go. Good job. That was example 5. Do we want to do one more? I mean, we've got 2 more examples, but they're graphing. You think you got this? We only got 4 minutes left. Okay, we're going to go with you got this. Okay? Have faith in you.